In the 1960s, two physicists, John Wheeler and Bryce DeWitt, tried to write an equation for everything. They wanted to connect the world of the very big, Einstein's general relativity, with the world of the very small, quantum mechanics. They were trying to create a single framework for the entire universe. What they ended up with was a mathematical monster. But it had a bizarre feature. In their final equation, the variable for time, the key that measures the ticking of the clock, was gone. It just vanished from the math. According to the Wheeler-DeWitt equation, at the most fundamental level, the universe is static. Nothing ever happens. This is the problem of time. It's a paradox that sits at the heart of modern physics. We experience time every second. We see change. We remember a past and anticipate a future. Yet the deepest description of reality we can muster suggests it might all be an illusion, a trick of perception. Our moon feels like that equation. It hangs in the sky, a seemingly timeless, unchanging object. It has been there for billions of years. It feels like a constant, but that quiet silver face hides a history of unimaginable violence and a set of mysteries that challenge our own origin story. Like the problem of time, the closer we look at the moon, the more the simple certainties disappear. The answers we thought we had about our nearest neighbor crumble, leaving only deeper, more baffling questions. And we thought landing there would solve everything. Instead, it just showed us how little we truly know. Number 15, the moon's dust is not normal dust. The Apollo 12 astronauts found a robotic probe on the moon. It was Surveyor 3. It had landed there 2.5 years earlier in April 1967. The astronauts, Pete Conrad and Alan Bean, were supposed to bring parts of it back to Earth. They wanted to see what the lunar environment does to man-made materials. When they got to the probe, they saw it was covered in a thin layer of dust. That was expected. What wasn't expected was that the dust had moved, the probe was sitting in a crater. The dust had somehow crept from the crater floor, up the side of the probe, and even into its components, moving against gravity. Back on Earth, scientists looked at the returned camera housing. They found tiny dust particles in places they had no business being. The dust was not inert, it was active. Lunar dust, or regolith, is one of the biggest unsolved problems for future lunar explorations. It is not like the dust on Earth. Earth dust is made of tiny, rounded particles. They have been worn down by wind and water for millions of years. They are relatively soft. The lunar dust is different. It was created by billions of years of meteorite impacts shattering rock. There is no wind or water on the moon to smooth the edges, so lunar dust particles are like microscopic shards of glass. They are incredibly sharp with jagged edges. They are also very fine. Some particles are less than 20 micrometers in diameter, smaller than the width of a human hair. This dust gets everywhere. During the Apollo missions, it clogged equipment. It abraded the astronauts' suits. Harrison Schmitt, the Apollo 17 astronaut and only geologist to walk on the moon, reported having a reaction to it. He called it lunar hay fever. He said it irritated his throat and eyes after he brought it inside the lunar module. The dust has a distinct smell, like spent gunpowder. No one knows exactly why. It might be the result of charged particles from the sun, the solar wind, hitting the lunar soil and creating a reactive surface that interacts with the moist air inside a spacecraft. But the real mystery is its movement. The moon has no atmosphere, it has no wind. Yet the dust moves. Scientists now believe the dust is electrostatically charged. During the lunar day, intense ultraviolet radiation from the sun knocks electrons off dust particles, giving them a positive charge. This charge can be strong enough to make the particles repel each other and levitate off the surface. They can float for meters, creating a kind of temporary low-lying dust atmosphere. This was hinted at in the 1960s by those surveyor probes. They saw a strange horizon glow just after sunset. There was a faint light lingering over the horizon. Some scientists now think this was sunlight scattering off a cloud of levitating dust. This creates a huge problem. If dust is constantly floating around, it could cover solar panels. It could work its way into seals and mechanisms, causing them to fail. It can get into habitats and lungs. The abrasive, glassy nature of the dust could cause long-term health problems for astronauts, a condition that might be called lunar silicosis. We don't know how high this dust can travel. Some models suggest that smaller particles can be lofted tens of kilometers high. There are even theories of, dust fountains at the Terminator, the line between day and night on the moon. At this line, strong electrical fields could be generated, shooting dust high into the lunar sky. We have sent people to the moon, we have brought back rocks, but we still do not have a complete understanding of the most common material on its surface. We don't know how it behaves, how it moves, or how dangerous it truly is. The dust itself is a dynamic alien environment we have only just begun to study. Number 14, the moon has two faces, and we don't know why. The far side of the moon was a complete mystery until October 7th, 1959. On that day, the Soviet Union's Luna 3 probe swung around the moon and took the first pictures of the side we could never see from Earth. The images were grainy, low resolution, and barely decipherable, but they revealed something shocking. The far side looked nothing like the near side. The man in the moon, those large, dark patches we see, was gone. The near side is dominated by vast, dark, smooth plains called maria or seas. These are ancient lava flows. About 17% of the near side is covered in them. The far side has almost none. Only about 1% of its surface is maria. Instead, the far side is almost entirely covered in craters. It is rugged, mountainous, and ancient-looking. The difference is not just cosmetic. It is geological. The crust on the far side is significantly thicker than on the near side. Our data from NASA's Grail mission, which precisely mapped the moon's gravity field in 2012, confirmed this. The far side crust can be up to 60 kilometers thick. The near side crust is, on average, only about 30 kilometers thick. This is a fundamental asymmetry that baffles planetary scientists. Why would one half of a celestial body be so different from the other? It is like finding a planet that is half ocean and half desert, with a sharp dividing line. There are several competing theories, but none are fully accepted. One leading idea involves the Earth itself. Shortly after the moon formed, it was much closer to Earth. The Earth was still a molten ball of rock glowing with incredible heat. Because the moon was tidally locked from the beginning, the same face always pointed toward this giant radiator. The near side was constantly baked by the Earth's heat, while the far side faced the cold of deep space. This temperature difference could have had a huge effect on the moon's formation. Elements that vaporize at lower temperatures, like aluminum and calcium, could have been cooked off the near side. They would have then condensed on the colder far side. These are the very elements that form the feldspar-rich rock that makes up the lunar crust. This process would have essentially piled extra crustal material onto the far side, making it thicker. A thicker crust would have made it much harder for magma from the mantle to erupt onto the surface, which would explain the lack of maria. Another more dramatic theory suggests Earth once had two moons. According to this model proposed in 2011 by scientists Martin Jutzi and Eric Asfog, a smaller second moon was caught in Earth's orbit along with our main moon. For tens of millions of years, they orbited together. Eventually, their orbits destabilized and they collided. But it was not a high-speed impact. It was a relatively slow-motion cosmic splat. The smaller moon would have spread itself across one hemisphere of the larger moon. Computer simulations show this could create the kind of thick, mountainous crust we see on the far side today. It would be a pancake of a moon plastered over half of our moon. A third possibility relates to a strange concentration of elements on the near side. There is a geological province on the near side called the Procellarum Creep Terranae. Creep stands for potassium K, rare earth elements REE, and phosphorus P. These are radioactive, heat-producing elements. Their concentration on the near side would have kept that region hotter for longer. This extra heat would have fueled the vast volcanic eruptions that formed the Maria and may have contributed to a thinner crust. But this just pushes the mystery back a step. Why are all these radioactive elements concentrated in one spot? It is like all the Earth's uranium being found in a single province. The two-faced nature of the moon points to a strange, lopsided event in its earliest history, and we are still arguing about what that event was. Number 13, the moon rings, like a bell. On November 20th, 1969, the Apollo 12 crew did something that created a new lunar mystery. After returning to their command module from the lunar surface, they intentionally crashed their lunar module, the ascent stage named Intrepid, back onto the moon. The crash site was about 72 kilometers from the seismometer they had just set up on the surface. They wanted to create a small, artificial moonquake to calibrate their instrument. The impact was equivalent to about 1 ton of TNT. The result was completely unexpected. Back in Houston, the scientists monitoring the seismometer were stunned. On Earth, a similar impact would cause vibrations that last for a few minutes at most. The ground, full of water and fractured rock, quickly absorbs the seismic waves. But the moon was different. The vibrations from the Intrepid crash just kept going. And going. The moon reverberated for over 55 minutes. The scientists at the press conference were giddy. One of them, Maurice Ewing, said, "As for the meaning of it, I'd rather not make an interpretation right now. But it is as though you had struck a bell, say, in the belfry of a church, a single blow, and found that the reverberation from it continued for 30 minutes. The phrase stuck. The moon rang like a bell. This happened again. The Apollo 13 mission, crippled by an explosion, had to use its lunar module as a lifeboat. They eventually jettisoned it, and it crashed into the moon with the force of 11 tons of TNT. This time, the seismometers left by Apollo 12 recorded vibrations that lasted for over 3 hours and traveled to a depth of 40 kilometers. Larger impacts from meteors were later recorded, with some moonquakes lasting for 4 hours. This strange seismic response led to some wild speculation. The most famous was the hollow moon theory. The idea was that the moon must be hollow, perhaps an artificial structure, because only a hollow object would resonate for so long. This idea is not taken seriously by scientists. We know the moon's density, and it is not hollow. It has a core, a mantle, and a crust, just like Earth. So why does it ring? The real answer is likely less sensational, but still mysterious. The key difference is water. Earth's crust is full of water and porous rock. Water is incredibly effective at damping seismic vibrations. It is like a shock absorber. The moon, for the most part, is bone dry, and its rock is not as fractured and crumbly as Earth's. The rock is hard and rigid, a result of being in a vacuum for billions of years. When seismic waves are introduced into this structure, there is almost nothing to stop them. They just bounce around inside the moon for a very long time, reflecting off the surface and the core. The low gravity of the moon also plays a role, allowing the vibrations to propagate more freely. So the moon is not a bell, but rather a massive, extremely efficient resonator. The bell analogy is about the duration, not the tone. But even this explanation has its own set of questions. The Apollo seismic data suggested the lunar crust was heavily fractured in the top few kilometers from constant meteorite bombardment. But below that, it was surprisingly solid. You know, how can the top layer be so shattered while, you know, the layers below are so rigid? The exact way these seismic waves travel through the moon is still not perfectly understood. The data from the Apollo seismometers, which operated until 1977, is still being analyzed today. They provided a brief, tantalizing glimpse into the moon's interior, an interior that behaves in a way unlike any geology we know on Earth. It showed us a world that is not dead, but one that shudders and vibrates in response to the slightest touch. Number 12, something massive is hiding under the South Pole. The largest impact crater on the moon is not visible from Earth. It is on the far side, and it is called the South Pole-Aitken Basin. It is one of the largest known impact craters in the entire solar system. It is enormous. The basin is about 2,500 kilometers in diameter and 13 kilometers deep. To put that in perspective, it stretches from the moon's south pole to a crater named Aitken, a quarter of the way across the moon. If it were on Earth, it would cover most of the United States. This basin was formed by a cataclysmic impact about 4.3 billion years ago. The object that hit the moon must have been colossal, perhaps 200 kilometers across. An impact of this size should have acted like a geological drill. It should have punched straight through the moon's crust and well into its mantle. Scientists expected to find vast amounts of mantle material exposed on the floor of the basin. This would be a scientific jackpot. It would give us a direct window into the moon's interior without having to drill. But when orbiters like the Galileo spacecraft and the Lunar Reconnaissance Orbiter LRO used spectrometers to analyze the composition of the basin floor, they did not find what they expected. There was some mantle material, but not nearly enough. The composition was still mostly crustal. It was a big puzzle. The impact was huge, but the geological wound seemed to have healed in a strange way. The mystery deepened in 2019. Scientists were analyzing data from NASA's Grail mission, which had mapped the moon's gravity, and the LRO, which had mapped its topography. They found something strange buried deep beneath the basin. There was a huge anomaly, a region of unexpectedly high mass. This blob of material is massive, estimated to be at least 2.18 quintillion kilograms. It extends down for more than 300 kilometers and is about 600 kilometers wide. It is so heavy that it is actually weighing down the floor of the basin, causing it to be several hundred meters lower than it should be. What is this giant, dense mass? Nobody knows for sure. The leading theory is that it is the metallic core of the asteroid that created the basin in the first place. When the giant object hit the moon, its dense, metal-rich core could have separated from its rocky outer layers and lodged itself deep within the moon's mantle. Computer simulations of such a large impact show that this is plausible. The metal core would have been suspended in the soft, hot mantle like a rock in a pool of honey, and it has been sitting there ever since. If this is true, it is an incredible find. It is the preserved heart of an ancient protoplanet that was destroyed billions of years ago. Another possibility is that the anomaly is not from an asteroid at all, but from the moon itself. After the impact, a vast ocean of molten rock would have filled the crater. As this magma ocean slowly cooled and solidified, dense oxides might have crystallized and sunk to the bottom, concentrating at the boundary between the crust and the mantle. This would also create a dense, heavy region that would match the gravity data. Both theories have their supporters. To solve the mystery, we would need to go there. A robotic lander or a human mission to the South Pole-Aitken Basin could collect samples and use seismic instruments to map out this hidden structure. Until then, one of the largest structures in the solar system remains hidden deep beneath the lunar surface, a gravitational ghost from a violent past. Number 11, the moon has strange, ghostly swirls. On the surface of the moon, in various locations, there are strange, beautiful patterns that look like they were painted with a brush. They are called lunar swirls. They are some of the most enigmatic and visually stunning features on the moon. They are bright, sinuous, and can stretch for hundreds of kilometers across the surface. They do not seem to be related to craters or any other typical geological feature. They have no height or depth. They are just patterns on the dust. The most famous of these is Reiner Gamma, a tadpole-shaped swirl in the Oceanus Procellarum that has been observed from Earth since the days of telescopes. For a long time, nobody knew what they were. Early theories suggested they were the remnants of comet impacts. The idea was that a comet, a mixture of ice and dust, would hit the moon. The gas and dust from the comet would scour the surface, creating bright patterns. This theory has largely been discarded because the swirls are so intricate and do not match the expected patterns of a comet impact. The real breakthrough came when we sent spacecraft to orbit the moon. Magnetometers on these probes discovered something incredible. Every single lunar swirl is located in a region where there is a localized magnetic field. The moon today does not have a global magnetic field like Earth does. But in some places, there are strong pockets of magnetism trapped in the crustal rocks. These are called magnetic anomalies. The swirls sit right on top of them. This connection is too strong to be a coincidence. The leading theory today is that these magnetic fields act as a kind of invisible shield. The moon is constantly being bombarded by the solar wind, a stream of charged particles from the sun. Over billions of years, the solar wind darkens the lunar soil. This process is called space weathering. But in the areas with magnetic fields, the field deflects the solar wind particles. They are steered away from the surface, so in these protected zones, the soil does not get weathered as much. It stays brighter than the surrounding areas. The swirls are, in essence, magnetic TANS lines on the moon's face. The dark lanes within the swirls are probably areas where the magnetic field lines are weaker or configured in a way that actually funnels solar wind particles onto the surface, darkening it even more. This is a good explanation for the appearance of the swirls, but it opens up an even bigger mystery. Where did the magnetic fields come from? The moon is too small and cooled too quickly to have ever had a long-lasting dynamo in its core like Earth does. A dynamo requires a liquid, convecting, electrically conductive core. The moon's core is small and mostly solid. Yet, we know the moon did have a magnetic field in the past. Apollo rock samples show that they were magnetized when they formed billions of years ago. So how did these isolated pockets of strong magnetism get there? One idea is that they are the remnants of the moon's ancient global magnetic field, which has since died. But it is hard to explain why they are so localized and strong. Another idea links them back to giant impacts. When a large asteroid or a comet hits the moon, the intense heat and pressure can create a superheated plasma cloud. This cloud can expand in the presence of even a weak background magnetic field, perhaps from the sun, and generate a powerful temporary magnetic field of its own. This field could have been strong enough to permanently magnetize the rocks as they cooled. This would explain why many magnetic anomalies are found antipodal to, or on the opposite side of the moon from, large impact basins. The seismic shock waves from the impact would have traveled through the moon and converged on the opposite side, creating the right conditions for magnetization. The swirls are a beautiful puzzle. They are the visible ghosts of a magnetic field that should not have existed, created by a process we are still struggling to understand. Number 10, the moon's water is in the wrong place. For decades, the moon was thought to be completely, utterly dry. The Apollo samples brought back from 1969 to 1972 seemed to confirm this. They were desiccated rocks. The intense heat of the moon's formation, especially in the leading giant impact theory, should have boiled away any water or other volatile compounds. The moon was the bone-dry world. This picture began to change in the 1990s. In 1994, a NASA probe named Clementine orbited the moon and used radar to scan its poles. It found data that suggested the presence of ice in the permanently shadowed craters near the South Pole. These are regions that have not seen sunlight in billions of years. The temperatures there are incredibly cold, as low as minus 240 degrees Celsius. They are some of the coldest places in the entire solar system. In 1998, the Lunar Prospector probe seemed to confirm this by detecting high concentrations of hydrogen, a key component of water, at both poles. The final confirmation came in 2009. NASA's Lacrosse mission was a spectacular experiment. They deliberately crashed the upper stage of their rocket into a permanently shadowed crater named Cabeus near the South Pole. A second spacecraft flew through the plume of debris that was kicked up, analyzing its composition. It found water. It detected a significant amount of water vapor and ice particles. Later, NASA's Lunar Reconnaissance Orbiter LRO and India's Chandrayaan-1 mission also confirmed the presence of water ice at the poles. We now know there is a lot of it, possibly hundreds of millions of tons. The mystery is not that the water is there. The cold traps at the poles make sense as a place for it to accumulate. The mystery is where the water came from in the first place. If the moon formed hot and dry, how did it get wet? The main theory is that it was delivered later. Over billions of years, comets and asteroids containing water ice have been crashing into the moon. Most of the water from these impacts would have instantly vaporized and been lost to space. But some water molecules would have bounced around the lunar surface until they fell into one of these super cold, permanently shadowed craters at the poles. Once there, they were trapped, frozen in place for eons. This is a good theory, but it may not be the whole story. In 2020, NASA's Sophia Observatory, an airplane with a giant telescope, detected water molecules on a sunlit surface of the moon, not just at the poles. It was not a lot of water, but it was there, trapped within mineral grains, protected from the harsh solar radiation. This discovery challenges the idea that all water must be in cold traps. It suggests water might be more widespread than we thought. Even more intriguing is the chemical signature of the lunar water. Analysis of Apollo samples has found tiny amounts of water trapped in volcanic glass beads from the moon's interior. The isotopic composition of this water, the ratio of different types of hydrogen, is very similar to the water found on Earth. It is different from the water found in most comets. This suggests that some of the moon's water may not have been delivered by comets at all. It might have been there from the very beginning. It might have come from, the Earth itself, transferred to the moon during the giant impact that formed it. But how could water survive such a cataclysmic high-temperature event? This is the water paradox. The moon has water. Some of it seems to have an ancient terrestrial origin, but our best theory for the moon's formation says that water should not be there at all. Reconciling the dry theory with the wet reality is one of the biggest challenges in lunar science. Number 9, the moon is drifting away. The moon is leaving us. Every year, it gets about 3.8 centimeters further away from the Earth. And that is about the same speed that your fingernails grow. This was measured with incredible precision using laser ranging experiments. The Apollo astronauts left retroflectors on the moon's surface. These are essentially sophisticated mirrors. Scientists on Earth can fire powerful lasers at these mirrors and measure the time it takes for the light to travel to the moon and back. This allows them to measure the distance to the moon with millimeter accuracy. And the data is clear the moon is slowly spiraling outwards. This is not a new phenomenon. It has been happening for billions of years. The reason is tidal friction. The moon's gravity pulls on the Earth, creating the ocean tides. As the Earth rotates, it tries to drag the bulging water of the tides along with it. This creates a tidal bulge on Earth that is slightly ahead of the moon in its orbit. This bulge of water has its own gravitational pull. It tugs the moon forward, giving it a little bit of energy. This extra energy pushes the moon into a higher, more distant orbit. At the same time, the moon's gravity pulls back on this tidal bulge. This acts like a brake on the Earth's rotation. The Earth is spinning slower and slower. The days are getting longer. When the moon first formed, a day on Earth was probably only about 5 or 6 hours long. For billions of years from now, a day will be much longer than 24 hours. The process is a transfer of angular momentum from the spinning Earth to the orbiting moon. The mystery here is not that it is happening, but what it means for the past. If we run the clock backwards, the moon gets closer and closer to the Earth. If you go back 4.5 billion years to when the moon is thought to have formed, the math becomes a problem. The current rate of recession, 3.8 cm per year, would place the moon inside the Earth only 1.5 billion years ago. We know the moon is much older than that, so the rate of recession must have been different in the past. Modeling the ancient tides is incredibly difficult. The arrangement of the continents on Earth dramatically affects the way the tides work. When the continents were arranged differently in supercontinents like Pangaea, the tidal friction would have been much less. So the moon would have receded more slowly, but how much more slowly? Geologists are trying to find answers by studying ancient rock formations. Some sedimentary rocks, called tidalites, preserve the patterns of ancient tides. By studying the layers in these rocks, they can try to calculate the length of the day and the distance to the moon hundreds of millions or even billions of years ago. One study from 2018 looked at 1.4 billion-year-old rocks from China and found that a day on Earth at that time was about 18.7 hours long. This would put the moon at a distance of about 341,000 kilometers compared to its current average distance of 384,000 kilometers. This data helps, but it is just one data point in a vast timeline. The further back we go, the more uncertain the models become. The lunar recession paradox is a complex puzzle that involves geology, physics, and astronomy. We know the moon is moving away, but we do not have a precise history of its journey. And if we do not know exactly how its orbit evolved, it makes it harder to be certain about how it formed in the first place. Number 8, the moon's orbit is all wrong. The moon's orbit around the Earth has a problem. It is tilted. The Earth orbits the sun on a plane called the ecliptic. Most of the other planets in the solar system also orbit on, or very close to, this plane. It is the flat, spinning disk that our solar system formed from. You would expect the moon to orbit the Earth in line with the Earth's equator. This is what most other large moons in the solar system do. They form out of a disk of material around their planet's equator, and they stay there. But our moon does not. Its orbit is tilted by about 5.1 degrees relative to the ecliptic plane. This might not sound like much, but for planetary formation models, it is a huge problem. It is very difficult to explain. The leading theory for the moon's formation is the giant impact hypothesis. This theory says that a Mars-sized object named Theia collided with the early Earth. The debris from this massive collision was thrown into orbit around the Earth and eventually coalesced to form the moon. The simplest version of this model predicts that the moon should have formed in a disk of debris right above Earth's equator. Its orbit should have zero inclination relative to the equator, but it has a 5.1 degree tilt relative to the ecliptic, which is even weirder. Over the years, scientists have tried to modify the giant impact theory to explain this tilt. One idea is that Theia did not hit the Earth head-on. It came in at a sharp, glancing angle. This could have thrown the debris into a tilted orbit, but the physics of this is complicated. It is hard to get the right amount of tilt without completely destroying the proto-Earth or giving the Earth-Moon system too much angular momentum. Another theory, proposed in 2015, suggests that the impact was much more energetic than previously thought. Perhaps the impact was so violent that it completely vaporized the proto-Earth, turning it into a giant, rapidly spinning donut of molten rock and gas called a synestia. The moon could have then condensed out of this vaporous donut. As the synestia cooled and contracted back into the Earth, the moon could have been pushed into a tilted orbit. This is a very new and speculative idea. A third set of theories suggests that the tilt was not there from the beginning. It was acquired later. Perhaps the moon's orbit was disturbed by gravitational interactions with other large objects that were flying around the inner solar system in its early days. Or perhaps there were complex resonances between the moon's orbit, the Earth's orbit, and the sun's gravity that slowly tilted the moon's path over millions of years. The 5.1 degree tilt is a stubborn fact that resists easy explanation. It is a critical test for any theory of lunar formation. A successful theory must not only explain the moon's size, composition, and lack of iron, but it also has to explain why it is in such a strange inclined orbit. The fact that we still struggle to do this shows that there is a fundamental piece of the puzzle missing in our understanding of how the Earth-Moon system came to be. It is a small number, 5.1 degrees, but it represents a giant hole in our knowledge. Number 7, the Moon's core is a strange misfit. For a long time, we did not even know if the Moon had a core. It is so small compared to the Earth that some scientists thought it might just be a solid ball of rock all the way through. The data from the Apollo seismic experiments was too limited to give a clear answer. It told us about the crust and the upper mantle, but the signals were too weak to probe the very center of the Moon. It was not until the 2010th that scientists, by reanalyzing the old Apollo data with modern computer techniques and combining it with new data on the Moon's rotation and gravity field, finally confirmed that the Moon does have a core. And it is a very strange one. The Moon's core is tiny. It is only about 330 kilometers in radius, which is about 20% of the Moon's total radius. For comparison, Earth's core is about 55% of its radius. The Moon's core is also not very dense. This is one of the key pieces of evidence supporting the giant impact hypothesis. The theory goes that when Theia hit the Earth, the dense iron cores of both bodies merged. The debris that was thrown into orbit to form the Moon was mostly made of the lighter, rocky mantle material from both Theia and the Earth. This is why the Moon has such a small iron core and a much lower overall density than Earth. The real mystery is the structure of this core. The best models we have today suggest it is a complex, layered structure. At the very center, there is a solid inner core made mostly of iron, about 240 kilometers in radius. This is surrounded by a liquid outer core, also mostly iron, about 90 kilometers thick. This liquid layer is what might have generated the Moon's ancient magnetic field. But outside of this liquid iron core is the weirdest part, a third layer. This is a partially molten boundary layer, perhaps 150 kilometers thick. It is not fully liquid and not fully solid. It is a kind of hot, gooey slush at the bottom of the lunar mantle. We have nothing like this inside the Earth. The boundary between Earth's liquid outer core and solid mantle is sharp. What is this strange slushy layer, and why is it there? Its existence suggests that the very center of the Moon is much more complex than a simple ball of iron. It might be a mixture of iron, sulfur, and other lighter elements. The way the Moon's mantle has been cooling over billions of years could have created this stratified, partially molten zone. It also tells us something about the Moon's thermal history. To have a liquid layer, even a partially molten one, the center of the Moon must still be quite hot, perhaps around 1,300 to 1,470 degrees Celsius. This complex layered core presents a challenge. How could such a small body retain enough heat for 4.5 billion years to keep a liquid layer in its core? The Moon should have cooled down and solidified much faster than the Earth. The presence of that gooey layer suggests a thermal history that we do not fully understand. The Moon's heart is not a simple, dead piece of iron. It is a complex, layered, and still warm engine that we are only just beginning to map. Number 6, the Moon used to have a powerful magnetosphere. One of the most surprising discoveries of the Apollo missions came from the rocks the astronauts brought back. When scientists analyzed these rocks in labs on Earth, they found that they were magnetized. The rocks contained a memory of a magnetic field, and it was not a weak one. The samples showed that when these rocks formed from cooling lava billions of years ago, they were in the presence of a magnetic field that was, in some cases, as strong as the Earth's magnetic field is today. This was a profound shock. The Earth has a magnetic field because it has a large, hot, convecting liquid iron core. This motion of liquid metal creates a dynamo which generates the field. The Moon is tiny. Its core is small, Planetary scientists did not think it was possible for the moon to have ever generated such a strong and long-lasting magnetic field. The evidence from the rocks is undeniable. Rocks from 3.9 to 3.6 billion years ago show a strong magnetic field. The field seems to have persisted, though it weakened over time, until about 1 to 2 billion years ago. Then, it died. Today, the moon has no global magnetic field. All that is left are those strange patches of crustal magnetism, the ones responsible for the lunar swirls. So, the great mystery is, how did the moon do it? How did this small world generate a powerful magnetosphere that lasted for over 2 billion years? There are a few competing theories, and none of them are perfect. The traditional core dynamo theory is the most straightforward, but also the most problematic. It suggests that the moon's liquid outer core was churning vigorously enough to create a dynamo. But what was powering it? On Earth, the dynamo is powered by both thermal convection heat rising from the solidifying inner core and compositional convection lighter elements being released as the core freezes. For the moon, it is hard to get the numbers to work. The core is so small that it should have cooled and solidified too quickly. A more exotic theory suggests that the dynamo was not powered from the inside, but from the outside. The rocky mantle of the moon could have been stirring the liquid core. In the moon's early history, it was much closer to the Earth. The powerful tidal forces from the Earth would have been sloshing the moon's liquid core around, providing the mechanical energy to power a dynamo. This is called a tidal stirring dynamo. As the moon moved further away from the Earth, these tidal forces would have weakened, and the dynamo would have eventually shut down. This fits the timeline reasonably well. Another idea involves giant impacts. The early moon was being heavily bombarded. A large impact could have changed the moon's rotation speed, or even knocked its solid mantle, causing it to precess or wobble differently from its liquid core. This differential motion between the mantle and the core could have stirred up the liquid iron and generated a magnetic field. This would mean the moon's magnetic field might have been intermittent, turning on and off in response to large impacts. We do not know which of these theories is correct. It is possible. It was a combination of factors. The moon's lost magnetic field is a major puzzle. It forces us to rethink how dynamos can work in small, rocky bodies. It tells us that for a time, the early Earth and Moon were a two-magnetosphere system, a much more complex and dynamic environment than we see today. The ghost of that lost field is still imprinted on every rock the Apollo astronauts brought home. Number 5. Moonquakes are deep, weird, and rhythmic. The Earth has earthquakes. They are caused by the movement of tectonic plates. The moon has moonquakes. But the moon does not have tectonic plates. So what is causing them? This is a question that the network of seismometers left by the Apollo missions tried to answer. From 1969 to 1977, these instruments recorded over 12,000 seismic events. They revealed that the moon is not a dead, quiet world. It is geologically active, but in a way that is totally alien to us. Lunar seismologists have classified moonquakes into 4 main types. The first are shallow quakes, which happen in the top 20 kilometers of the crust. These are the most powerful, reaching up to 5.5 on the Richter scale. They can last for a long time, over 10 minutes. We only recorded 28 of them, and we still do not know what causes them. They might be caused by the crust shifting and cracking under the strain of tidal forces from the Earth, or from the slow, long-term cooling of the moon. The second type are the vibrations from meteorite impacts. These are predictable and help scientists study the structure of the crust. The third are thermalquakes. These are very small tremors that happen as the frigid lunar crust expands when it is hit by sunlight after the 2-week-long lunar night. The Apollo 17 seismometer detected these little creaks and groans every lunar morning. But the fourth type is the most mysterious and the most common. These are deep moonquakes. They occur very deep inside the moon, about halfway to its center at depths of 800 to 1,000 kilometers. They are not very strong, usually less than 2 on the Richter scale, but they are incredibly strange for 2 reasons. First, they are not random. The deep moonquakes happen in very specific locations. The Apollo network identified about 100 different nests or clusters where these quakes originate. It is as if there are specific stressed points deep within the lunar mantle that are breaking over and over again. Second, they are tidal. The deep moonquakes are not random in time either. They have a predictable rhythm. They occur at the same point in the moon's monthly orbit around the Earth. They happen most often when the moon is at its apogee farthest from Earth and perigee closest to Earth. This is when the tidal stresses from the Earth's gravity are at their maximum. The Earth is literally squeezing and stretching the moon, and these deep nests are the points that fracture in response. This is a profoundly weird phenomenon. On Earth, once a fault slips and causes an earthquake, the stress is relieved, and it takes a long time, often hundreds of years, for the stress to build up again. On the moon, these deep faults seem to be re-breaking every single month in a predictable cycle. It is as if the rock deep inside the moon is not brittle like Earth rock, but is somehow being stressed to its breaking point and then healing itself over and over. We do not know what kind of geological structures could cause this. The pressure and temperature at those depths are immense. And what kind of rock can repeatedly break in such a rhythmic way? The Apollo seismic network was not large enough to pinpoint the exact mechanisms. To truly understand deep moonquakes, we would need to place a much larger, more sensitive network of seismometers all over the moon. Until then, we are left with the strange knowledge that the moon's heart beats with a tidal rhythm, a deep, slow pulse driven by the pull of the Earth. Number 4. The moon's mantle is missing. When the Apollo astronauts brought back 382 kilograms of lunar rocks, geologists on Earth were ecstatic. For the first time, they could study pristine samples from another world. The rocks were mostly of 2 types. There were basalts from the dark volcanic Maria, and there was anorthosite from the bright, heavily cratered highlands. The anorthosite is the original crust of the moon. The basalt is younger lava that erupted onto that crust. Geologists have a standard model for how rocky planets form. They start as molten balls. As they cool, heavy elements like iron and nickel sink to the center to form a core. The lighter elements float to the top to form a crust. In between is the mantle, which makes up the bulk of the planet's volume. The mantle is typically rich in minerals like olivine and pyroxene, so scientists expected to find 3 main types of rock in the Apollo samples: crustal rock, anorthosite, mantle rock, olivine rich, and rocks that are a mixture. They found plenty of crustal rock. They found plenty of volcanic basalts that came from the melting of the upper mantle, but they found almost no pure, pristine samples of the mantle itself. The rocks that should make up the vast majority of the moon's interior were conspicuously absent. This is the missing mantle problem. We know the mantle must be there. We can model its existence from the moon's density and seismic data. The lavas that formed the Maria had to come from the melting of the mantle, but we do not have a clean piece of it. It is as if someone gave you a cherry pie, but you only got the crust and the filling, not the fruit itself. Why is this? One possibility is just bad luck. The 6 Apollo landing sites were all on the near side of the moon. Perhaps they just did not land in a place where deep mantle material had been excavated by an impact. A truly giant impact, like the one that formed the South Pole-Aitken basin, should have dredged up plenty of mantle rock. But we have not yet sent a mission to sample that basin. Another idea is that our understanding of the lunar magma ocean is incomplete. The standard model says that as the early molten moon cooled, the lighter plagioclase feldspar, which makes anorthosite, floated to the top to form the crust, while the denser olivine and pyroxene sank to form the mantle. But perhaps the process was messier. Maybe the mantle never formed into clean, distinct layers. that could be easily excavated. Maybe it is more of a jumbled mix, a cumulate pile that is not easily recognizable as pure mantle rock. Some small green glass beads found in the Apollo 17 samples are thought to be from volcanic fire fountains that erupted from very deep within the moon, over 400 kilometers down. These could be our most direct samples of the deep mantle, but they are tiny beads, not solid rocks. The missing mantle is a frustrating problem. Without actual samples, our models of the moon's composition and internal structure are based on inferences and remote sensing, not on-ground truth. The mantle is the engine of lunar geology. It is the source of its volcanism. It is where moonquakes originate. Not having a piece of it is like trying to understand a car engine without ever being able to look under the hood. It remains one of the highest priority goals for future sample return missions. Go find a piece of the moon's missing heart. Number 3, a strange layer of elements is in the wrong place. There is a strange geological feature on the moon that is unlike anything else in the solar system. It is called the Procellarum Creep Terran. It is a vast region on the near side of the moon, centered on the Oceanus Procellarum Ocean of Storms and Imbrium Basin. What makes this area special is its chemical composition. It is highly enriched in a strange cocktail of elements. The name CREEP is an acronym. It stands for Potassium K, Rare Earth Elements REE, like samarium, europium, and gadolinium, and phosphorus P. These elements, along with other radioactive, heat-producing elements like thorium and uranium, are all concentrated in this one massive province. The concentration of thorium in the CREEP terrain is 50 times higher than in the Farside Highlands. This is a profound mystery. On Earth, these kinds of elements are spread more or less evenly throughout the planet's crust and mantle. Why on the moon are they all gathered together in one giant patch on the near side? The existence of CREEP is deeply tied to the magma ocean hypothesis. The elements that make up CREEP are incompatible elements. This means that as the magma ocean cooled and minerals started to crystallize, these elements did not fit neatly into the crystal structures. So they were left behind in the remaining liquid melt. As the moon solidified from the bottom up, this CREEP-rich liquid would have been concentrated into a final gooey layer sandwiched between the crust and the mantle. This explains how CREEP was formed, but it does not explain why it all ended up on the near side. The final layer of molten CREEP should have been a global spherical shell. So what happened to make it so lopsided? This mystery is connected to the mystery of the moon's two faces. The radioactive elements in CREEP potassium, thorium, uranium produce heat as they decay. The massive concentration of these elements on the near side would have acted like a giant electric blanket, keeping that side of the moon warmer for longer. This extra heat would have fueled the prolonged period of volcanism that created the near side Maria. It could have also contributed to, the thinner crust on the near side. The CREEP is the smoking gun for the moon's asymmetry. So, why is it there? One theory links it to the giant impact that formed the Imbrium Basin, one of the largest on the near side. This colossal impact could have punched through the crust and dredged up the CREEP material from the layer below, splattering it all over the region. The problem with this theory is that CREEP seems to be spread over a much larger area than just the Imbrium Basin. A more comprehensive theory goes back to the formation of the moon's crust itself. Perhaps the crust did not form uniformly. As the anorthosite crust solidified over the magma ocean, a massive impact, maybe the one that formed the South Pole-Aitken basin, could have effectively knocked the entire solid crust to one side. This would have scraped all of the final CREEP-rich liquid into one big pool on the opposite side, which just happened to be the near side. The Procellarum Creep Terran is the key to understanding the moon's entire geological and thermal history. It explains why the near side is so different from the far side, but the origin of the Creep terrain itself remains one of the biggest unsolved puzzles in planetary science. It is a chemical anomaly the size of a continent, and we do not know how it got there. Number 2, the moon's age is a paradox. How old is the moon? The standard answer is about 4.51 billion years old. This age comes from dating the Apollo rock samples and from models of solar system formation. The general consensus is that the giant impact that formed the moon happened very early in the solar system's history, perhaps 30 to 50 million years after the sun itself formed. The moon then took some time to cool and solidify from its molten state, but recent studies have thrown a wrench into this tidy timeline. The problem is that the moon seems to have solidified its crust very, very quickly. The anorthosite rocks from the lunar highlands, which make up the primordial crust, have been dated to be incredibly old. They formed from the lunar magma ocean. For them to exist, the entire moon, or at least its outer layers, had to be a sea of molten rock. In 2017, a team of scientists reanalyzed the Apollo samples. They did not look at the age of the rocks themselves, but at the age of the chemical differentiation of the moon. They looked at the isotopes of elements like tungsten and hafnium, which separate in specific ways when a planetary body separates into a core and a mantle. Their results suggested that the moon's magma ocean was still solidifying as late as 150 to 200 million years after the formation of the solar system. This would make the moon significantly younger than the standard age. This is the late formation model. However, another line of evidence points in the exact opposite direction. This evidence comes from tiny crystals of the mineral zircon. Zircon is a geologist's dream. When it crystallizes, it traps uranium atoms but rejects lead. Uranium decays into lead at a very precise known rate. By measuring the ratio of uranium to lead in a zircon crystal, you can determine its age with incredible accuracy. Scientists found tiny zircon crystals in the Apollo 14 samples. In 2017, a detailed study of one of these crystals dated it to be 4.51 billion years old. This crystal would have formed as the magma ocean was solidifying. This date suggests the moon formed and cooled very early, just as the standard model predicts. This is the early formation model. So we have a paradox. Some isotopic systems suggest a young moon that formed late and took a long time to cool. Other data from the zircon clocks suggest an old moon that formed early and cooled very quickly. How can both be true? This has led to a major debate in the lunar science community. The problem might be with our assumptions. Perhaps the giant impact did not create a completely molten moon. Maybe it was only partially molten, which would complicate the cooling timeline. Or perhaps the Apollo samples are not representative of the entire moon. We have only sampled a few small locations. Another radical idea suggests the magma ocean did not cool uniformly. Maybe the crust solidified very quickly, forming the ancient zircons, but pockets of magma remained deep inside for another 100 million years, which would explain the younger isotopic signatures. The age of the moon is not just a piece of trivia, it is fundamental to understanding the entire history of the Earth and the inner solar system. The giant impact was the most significant event in Earth's history after its initial formation. It shaped our planet's rotation, tilt, and possibly even the development of life. If we do not know when it happened, our timeline for the first few 100 million years of Earth's existence is shaky. The clocks in the lunar rocks are telling us conflicting stories, and we do not yet know how to read them correctly. Number 1, the giant impact theory is full of holes. The most fundamental mystery about the moon is the most basic one. Where did it come from? For the last few decades, the answer has been the giant impact hypothesis. The story is compelling. Early in the solar system's history, a Mars-sized protoplanet, which we call Theia, slammed into the proto-Earth. The collision was cataclysmic. It melted both bodies and threw a vast cloud of vaporized rock and debris into orbit. This debris ring then coalesced to form the moon. This theory explains a lot. It explains why the moon is so large compared to the Earth. It explains why the moon has such a tiny iron core. The iron from both Theia and Earth would have merged and stayed with the larger body. It explains the high angular momentum of the Earth-Moon system, and it explains why the moon's rocks are bone dry, as the heat of the impact would have vaporized any water. It is a beautiful and elegant theory, and it is probably wrong, at least in its simplest form. The biggest problem is something called the isotopic crisis. Every planet and body in the solar system has a unique chemical fingerprint, a specific ratio of isotopes of elements like oxygen, titanium, and tungsten. These isotopes are like a planetary DNA sequence. We have analyzed rocks from Mars and from various asteroids, and they all have different isotopic fingerprints from the Earth. The giant impact theory says the moon was formed mostly from the debris of Theia. Therefore, the moon should have a different isotopic fingerprint from the Earth, and it should look like a mixture of Earth and Theia, but it does not. When scientists analyzed the Apollo samples, they found that the moon's isotopic fingerprint for almost every element is virtually identical to Earth's. The moon looks like it was made entirely out of Earth's mantle, with no contribution from Theia at all. This is a devastating blow to the simple version of the theory. How can the moon be made of Earth material when it was Theia that did the hitting? This has forced scientists to come up with more and more elaborate versions of the giant impact model. One idea is that Theia just happened to have the exact same isotopic fingerprint as Earth. This is considered highly unlikely. It would be like finding a random person who is your identical twin but is completely unrelated to you. Another idea is that after the impact, the molten debris disk of the proto-Earth and the proto-Moon were connected by a vapor atmosphere for thousands of years. This would have allowed them to mix thoroughly, evening out their isotopic signatures before the moon fully formed. This is plausible, but the physics is very complex. A more violent solution is the synestia hypothesis mentioned earlier. In this model, the impact was so energetic that it did not just create a debris disk. It completely vaporized both Theia and most of the Earth's mantle, forming a single, massive, rapidly spinning donut of vaporized rock called a synestia. The moon would have then condensed from this well-mixed vapor, which is why it has the same isotopic signature as the Earth. The Earth would have later reformed as the synestia cooled. This solves the isotope problem, but it requires a much more energetic and specific type of impact. The giant impact theory has another major problem, the volatile paradox. The theory predicts a hot, violent formation that should have boiled off all volatile elements like water, zinc, and potassium. But as we have learned, the moon is not completely dry. It has water, and analysis of Apollo samples shows it has more volatile elements than it should. How did they survive the inferno of the moon's birth? The origin of the moon is the cornerstone of our understanding of our own planet's history. The giant impact hypothesis is the best idea we have, but it is creaking under the weight of contradictory evidence. The isotopic similarity, the presence of volatiles, the strange orbital tilt, all point to the fact that the story is far more complex than a simple collision. The moon is so familiar, so constant in our sky, yet the story of its birth remains the greatest unsolved mystery of our celestial neighborhood. It is a piece of the Earth, yet not of the Earth, and we still do not know why.